So let's look at one problem involving salts. So in this particular problem, you have sodium chlorobenzoate, 0.20 molar solution of it, with a pH of 8.65. Now you're asked to calculate for its conjugate acid, the pH of 0.20 molar of chlorobenzoic acid. Now I did say that again, sodium chlorobenzoate should be the conjugate base of chlorobenzoic acid. But in particular, what I'm talking about is when benzoic acid or chlorobenzoic acid dissociates in solution or gives up an acid in solution, the formula should be C6H4 ClO2. Okay, and that acidic proton here is given up, let's say, to water. Okay, and that's going to form H3O plus, okay, plus C6H4 ClO2 minus. Okay, and this is the basic part of sodium chlorobenzoate, which as a salt again dissociates also in solution, C6H4 ClO2. Okay, so it dissociates into solution as sodium plus and C6H4 ClO2 minus. Okay, now let's just label that as conjugate acid or conjugate base and weak acid. Okay, now remember that for rules of determining the natures of salts, since sodium here should have been from strong acid such as NaOH, okay, then sodium plus as a cation does not have any acidic properties, okay, because again it is the conjugate acid of a really strong base. But for the benzoic ion, which is the conjugate acid, or sorry, conjugate base of chlorobenzoic acid, a weak acid, then this should have some basic properties. So therefore, sodium chlorobenzoate is basic. And if you're not convinced, you're given that the pH of the solution is 8.65. Okay, so from this information, we therefore know, or that's why we know that sodium chlorobenzoate and chlorobenzoic acid are conjugate acid-base pairs. Now notice here that we're not given either the Ka value of chlorobenzoic acid or the Kb value of sodium chlorobenzoate, but we're given the pH of the conjugate base. Okay, so therefore we should be able to write a nice table for this one. Okay, now again, for sodium chlorobenzoate, sodium is not really an active part of the solution. It's not an active species. So we can say that the only one which actually undergoes an acid-base reaction is the chlorobenzoate ion. And I'm just going to abbreviate that as Cb minus, meaning chlorobenzoate, and then I'm going to call chlorobenzoic acid as HCb. Okay, so if we write an equilibrium expression for this, we will have chlorobenzoate ion. I'm not writing here the phases anymore to save some time. Okay, plus water. Okay, will give you chlorobenzoic acid plus hydroxide. Okay, again here the concentration of sodium chlorobenzoate should just give you also the concentration of the benzoate ion. So for the ice table, the initial concentration of benzoate ions should be 0.20. Okay, we ignore water, and then we start with 0 of chlorobenzoic acid and 0 of hydroxides. Okay, we actually have a change in x as the system goes into equilibrium. Ignore again, plus x, and then this one should be 0.20 minus x. This one should be x at equilibrium, and then this x. Okay, so before we proceed, keep in mind that you have a pH of the solution which is 8.65. Okay, remember that the pH actually tells you the concentration of hydronium ions. Now since chlorobenzoate is a weak base, so instead of actually using the pH to determine what the hydronium ion concentration is, we can use it to solve for pOH, and then eventually we can determine the concentration of hydroxides at equilibrium, which is just basically equal to X. I guess what I'm trying to say here is, from this pH, you can determine what the concentration of hydroxides are at equilibrium. Okay, so this one should just be pOH is equal to 14 minus 8.65. Okay, and the pOH therefore is equal to 5.35. Okay, and therefore the OH concentration should be OH is equal to 10 to the negative 5.35, and therefore the hydroxide concentration after solving that should be equal to 4.5 times 10 to the negative 6, and again that's equal to X. Okay, now we can substitute this value in here and here, and not really necessarily, but we can also do it there. Okay, again it's not really necessary because if you notice, this one is times 10 to the negative 6, and then this one is 0.2. Okay, but we'll just do that for the sake of doing it. Okay, so therefore the Kb expression, again we still don't know what Kb is. Kb expression should therefore be 4.5 times 10 to the minus 6. Okay, that's the concentration of chlorobenzoic acid times 4.5 times 10 to the minus 6, alright, divided by 0.20 minus 4.5 times 10 to the minus 6. Okay, and then this will just simplify into 2.025 times 10 to the negative 11 divided by, again, roughly 0.2 if you do the math. Okay, and then this will just give you 1.01 times 10 to the negative 10. Okay, and then from there we are actually trying to solve for the pH of chlorobenzoic acid. Okay, now that we have the Kb of chlorobenzoate, from there we can actually solve for Ka. Okay, remember that they are both they are conjugate acid-base pairs. So Ka should just be equal to Kw divided by Kb. So that should be 1.0 times 10 to the negative 14 divided by 1.01 times 10 to the negative 10. Let me just rewrite this. Okay, and this will give you 1.0 times 10 to the negative 4. Alright, and then the next thing that we have to do is set up a nice table for chlorobenzoic acid. So that will be chlorobenzoic acid plus water, okay, going to yield hydronium ions and the benzoate ion, chlorobenzoate ion that is, and then this is MiCe. Keep in mind that these are two separate solutions. Okay, so this one should be 0.20. Now I did say they were separate solutions because here you should begin with no concentration of chlorobenzoate. Okay, and then this one should be minus X plus X, and then this one should be plus X. This one is 0.20. Okay, and then this one is X, then this one is X. Okay, but again let's assume that this is equal to 0.20. Oops, this is actually 0.20 minus X, but again let's assume that that is 0.20, that X is negligible. Okay, so from there we can set up an equation for Ka that will be 1.0 times 10 to the negative 4 is equal to X times X divided by 0.20. Okay, that will just give us X is equal to 4.5 times 10 to the negative 3 molar, which is basically the hydronium ion concentration. Okay, but again let's check if our assumptions are valid. So check first, calculate for percent dissociation. and that will just be equal to 4.5 times 10 to the negative 3 molar divided by 0.20 molar, okay, times 100%. We have a percent dissociation equal to 2.25% or 2.3%, which means that our assumptions are good. You don't have to do the quadratic formula anymore. And then now, since we have a concentration of hydronium ions, we can use this value to calculate for pH. So therefore pH is equal to negative log of that number, 4.5 times 10 to the minus 3 molar. And if you do the math, you will get 2.35 as pH. All right.